So let's start from powder. Powder preparation by first mechanical method, very simple. Comminution. Comminution, which means just mechanically crushing. Make the powder particle size smaller, okay? Using mechanical force. Crushing, grinding, milling, whatever, to make the powder from larger size to smaller particle size, okay? Or the larger size could even be gravels, which means really large, like stone. Okay, you mind it. The core size reduction going from really large, you can really see it, size like your fingernail sized. You just crush them, okay? And reducing the particle size from whatever you got, you milled, to 10 millimeter. What size is that? Like your size of your nail, right? 10 millimeter or 0.1 millimeter, something like that. You using equipment such as jaw gyration or some cone crusher. I'm having a small animation. It's just a mechanical crusher. The center part moves back and forth surrounding. The outside is fixed and crushing the big, actually gravel, large stone pieces into much finer 10 millimeter sized stones. Make sense? That's just the core size reduction. And then fine size reduction. After you get like 1 millimeter around the particles, you are using something, some equipment to further reduce them into micron range. Okay? Fine size reduction. Quite often you request them for, well, many cases. Use various milling technique. We'll just quickly talk them. For example, roller mill or jet mill. I'm showing here high pressure roller mill. Essentially two roller rotating. You fix the gap between them and you feed large particle through them, and through the crushing you get the large particle into finer ones. Okay, two rows, compact pressure, megapascal. That's quite often enough to crush many ceramic particles on the 100 megapascal range. Okay. And the advantage is good energy utilization and low wear. Of course, you don't get too fine particles, like 100 micron size, 10 to 100 micron size, because you cannot really make the two cone to be too close to each other. Okay, otherwise it just doesn't work. The other one is called jet milling. You are feeding powder and you are providing high-speed gas. Okay, and the powder themselves crush onto each other and get smaller. Jet milling. High-speed gas flow carry them to make coarse particle into finer ones. Will just advantage rapid, quick, down to 1 micron. Can have low contamination, 1 to 20 micron jet mill. Sometimes people use it. Okay, ball mill, which in the lab we use a lot. We are showing different so-called grinding media, or essentially different sized of balls. Okay, could be a really literally a sphere, or could be kind of cylindrical shaped, rounded cylindrical shaped. Okay, using grinding media to produce compression impact, and together between the heating crushing among the balls, the powder also got crushed into smaller particle size. Down to 0.5 micron, you can crush the powder down to around 0.5 micron. That's enough for many technical applications. Okay, the running speed, well, it depends on the running speed. How fast it depends on running speed. Running at a low speed has large balls that depend on the potential energy. The things drop the balls. Those running at a really high speed, you are using the essential kinetic energy. Grinding medium material, we said the white ones are quite often zirconium dioxide, which is pretty hard material. And people can also use quite often steel ball, hardened steel ball, very cheap. Okay, or sometimes you find what is this? Tungsten carbide balls. Okay, very hard material. Okay, these are the common ones. The ball size depending on your need. The smaller balls leads to more collision, intercollision, and higher grounding ratio, but you cannot use too small. If the balls are too small, they have too little kinetic energy when they impinge, and that also doesn't crash. So it's a balance. Smaller balls help you, but cannot be too small. Okay. Particle size we said down to 0.5 micron. Okay, and as the particles start from cores, as you grind them further and further and further, it getting slower and slower to reduce their particle size further. Make sense? It's just getting more and more slower. It's probably very fast to get from 50 micron to 5 micron, but it's getting slower from 5 micron to 1 micron, and even slower from 1 micron to like 0.5 micron. You have to use longer and longer time. And with longer time, that comes the issue of contamination. Make sense? If you mill it for too long, if your material is hard, it may grind some of these stuff into it, like steel or whatever. Okay, so that's a balance. Okay, the other one is wear of grinding media. You wear too much, the material itself the balls itself got consumed. Okay, tumble ball mill. Tumble ball mill is, as we said, tumble. Just like what we show here, the jar is rotating and you put the ball inside, and as it rotates, centrifuge, the ball may be thrown up, and halfway at the top it may drop down. Okay, tumble ball mill, and in this process that's impacting between the balls to crush the powders. Low speed rotation, not very high, quite often, probably 60 per minute, 100 per minute, something like that, or 200. Not too fast. Rotating this is not too fast. This is lab scale. This can be industry scale. Okay, grinding media balls cause impact breakage of the powders. And the critical speed reached when the centrifuge force balance gravity. Okay, when the centrifuge force balance gravity. Okay, and the typical operated at 75% of the critical speed. Here I'm talking about the frequency. Centrifuge, that's the frequency. How many revolution per second or per minute? In this case, probably per second. Okay, that gives you a critical equation to calculate critical. The A means what? No, not acceleration. Yeah, the radius for this guy. Okay, G is gravity, acceleration. Okay, and dry milling loading level. How much we should load? This is nothing precise. For mechanical engineer, this is nothing precise. Quite often we would say, okay, when you ball mill the media, the balls takes up roughly 50% of your container, which means you have a big container, half of the volume would go to the ball. Of course, you cannot pack dense, it's just ball. There will be gap in between. And the powder would be roughly half of the ball, roughly half of the ball. Okay, that's for dry milling. Dry milling means within the container, it's just the balls, the media, and the powder. Yeah, whatever powder. Of course, you can also do wet milling, more uniform. Okay, more uniform, but sometimes you have to add extra step of drying the solvent. Okay, and in this case, still the media 50%, the slurry roughly 40% of the container, and the slurry is typically 25 to 40 weight percent. And you ask me, Dao Chen, what is the optimum? I said, hard to say. That's no optimum. As long as you are roughly in this range, it's okay. You see that? It's not precise. Okay. What if I'm 49%? What if I'm 51%? Doesn't matter. for these types of processing. Make sense? Because what are you doing? I'm only trying to crush powder from larger size to smaller size. I'm not trying to shoot a specific number. Very crude. Okay? So let's stop here. Okay, so let's continue. The other one is called plenary ball milling. This is what the machine looks like. Plenary ball mill. Okay, essentially it's using jar holding grinding media together with the powder. Santano probably can demonstrate you in the seismic lab, and move within a plane like a planet with two types of rotation. Remember, the Earth rotate by itself around its own axis, but at the same time around the sun, plenary milling. So that's what it looks like. Two types of rotation. One is the jar by itself rotating along the jar's own axis. At the same time, the jar rotates around a center, like a planet around the sun. Okay, two types of milling, one around the jar, one around the orbit. Lab scale only. You do this only for lab scale. Symmetrical jar placement. Make sense? Like if we have 4, if we are putting a lot of stuff here, where are you going to put the next? Definitely symmetrical, right? May put them in symmetrical position so that it's balanced by weight and stuff. Simple for mechanical engineer, right? That's common sense. Okay. And other types of milling technique, very simple, vibration mill. So we put in here a lot of the grinding media and powder, and everything just vibrate. 10 hertz, not very high frequency, but everything shake in 3D, up, down, front, and back, shake. And during this process, the grinding media will gradually crush the powder. Okay, not rotation. Grinding media occupies cylindrical shape, 90% of the volume. High impact energy compared with tumble mill. Okay, the other one is important called attrition mill or stirred media mill. Stirred media mill. What does that mean? It means okay, you see this stirrer. You put this bar into a container, but this bar has side branches, and then all these balls, as you rotate, the bar is going to stir up the media, the balls, and that would help further the balls to crush the powder in between. This is called a attrition mill. Grinding media stirred vigorously. Typically, wet milling, which means you have to add some solvent in there, and a very high efficiency. You can grind down to the balls are 0.2 to 10 millimeter in size, very high efficiency, very effective to reduce the particle size. Okay,